Welcome to Electron. Now we're going to take a look at a series circuit and what we also call a voltage divider. Here we have a 20 volt source. Here are the output terminals of the source. Also notice that we've connected the negative end of the voltage source to ground, which means we force that to be 0 volts. And now what we're trying to determine is what is the voltage drop across V1 and what is the voltage drop across V2. V1 is the voltage drop across R1 and V2 is the voltage drop across R2. The reason why we call this a voltage divider is because we can take a 20 volt source and with a combination of two resistors like this, determine or turn this into a lower voltage onto which we can actually put a other load. For example, we could put a load resistor. Let me try that better here. There we go. Here's my load resistor. We could put a load resistor on V2 if the load resistor requires a voltage less than the 20 volts. And by picking the right combination of R1 and R2, we can then make this to be the correct voltage for the particular reason that we want it for. The way we do that is we first find the total resistance in the circuit. Our total, in this case, since it's a series circuit, is simply the sum of the two resistors, R1 plus R2, which is equal to 4 ohms plus 6 ohms, which is equal to 10 ohms. From that, using Ohm's law, we can find the current in the circuit. So the current I can be determined using Ohm's law to be the voltage applied divided by the total resistance. In this case, that's 20 volts divided by 10 ohms, which is equal to 2 amps. So the current here is equal to 2 amps. Now we can find the voltage across R1 and the voltage across R2. Again, using Ohm's law, we can then take this equation. We can take I equals V over R and write it as V equals I times R. So the voltage across any resistor is simply the current through the resistor times the resistance. V1 is equal to R1 or I1, so I times R1, which is 2 amps times 4 ohms, which is 8 volts, and V2 is equal to I times R2, which is equal to 2 amps times 6 ohms, which is equal to 12 volts. Which means, since A must be at 20 volts, because this end of the voltage source is 20 volts higher than this end, which is at 0 volts, that makes this at 20 volts. Then we have V1, an 8 volt drop, 20 volts minus 8, puts this at 12 volts. So this is at 20 volts, this is at 12 volts. And then we have a 12 volt drop across R2 from 12 down to 0 volts. This, of course, should be the same as the voltage over here because this is a single node right here which is attached to ground. What that means now is that we have a voltage divider where we took 20 volts and divided into 8 volts and 12 volts. And if we want the load resistor to be connected to 12 volts, we have the right voltage divider, and this then provides the 12 volts for the load resistor. This is the technique that is often used in circuitry on circuit boards. What do we do with the other 8 volts? Well, we can utilize the 8 volts, or we can simply say we don't need it, we don't need to attach anything to it. We were just interested in taking a 20 volt source and bringing it down to 12 volt that we can apply to a load resistor, and that's what we're after. One more quick note on this. Another way of dealing with voltage dividers, if, for example, we want a specific voltage right here, volt 2, that can be written as the voltage applied by the voltage source times the ratio of R2, the resistance across this particular connection, divided by the sum of the two resistors. In this case, V2 is equal to the 20 volts times the ratio of 6 ohms divided by 4 plus 6 ohms, 4 ohms plus 6 ohms. 6 divided by 4, 4 plus 6, that's 6 divided by 10, or 20 volts times 6 over 10, which is equal to 12 volts. So that's another way in which you can look at a voltage divider simply by using this equation right here. We can determine what combination of resistors we need to come up with the correct voltage on our voltage divider. That's how it's done.